So I'm really excited to tell you about some of the recent work we've done on using machine learning for scientific discovery. The title is comma with examples in fluid mechanics. So depending on the audience, sometimes I talk more about the fluid, sometimes I talk more about the discovery. I think here I'm going to talk more about the, this pointer is going to be hard to get used to, the scientific discovery. Before starting, I want to acknowledge a number of excellent co-authors and collaborators on this work. So almost all of the dynamical systems work is with people on the left. Almost all of the fluids work is with people on the right. So I'm going to highlight some vignettes throughout this talk, especially from our excellent postdocs and PhD students. If you're interested in fluid mechanics in particular, you can kind of have a deep dive of machine learning for fluid mechanics in this annual review paper. The way I think about it, pretty much any system, I like fluids because it is the prototypical high-dimensional, nonlinear, multi-scale problem, or at least one of the. And so if you have a problem that has high dimensions, multi-scale physics in space and time that's nonlinear, like neuroscience, epidemiology, molecular dynamics, I think a lot of kind of the tools are transferable here. And so we've taken a lot of inspiration from you all, and hopefully there's some, we can give back a little too. And the reason that we think it's possible to do data-driven fluid mechanics and machine learning both rely on the fact that there are patterns in your data. Okay, so this is kind of the cornerstone of machine learning for fluids. This has been an effort, at least since the 1970s, to leverage the huge and growing wealth of data that we have in computational and experimental fluid dynamics. You'll notice this is the cloud flow. This is a satellite image of cloud flow forming over Guadalupe Island. This flow is more complex than we can simulate on the world's largest supercomputers, at least to capture every single scale of this flow. But you can see these very, very strong patterns emerging. This is a low-dimensional Kármán vortex street. You could probably describe this flow with 3 or 4 or 5 degrees of freedom pretty accurately. Okay, and so this is something we've been doing for a long time in fluids, and now with kind of emerging techniques, we're able to do a lot more. If you want to learn, again, more about how this works specifically in the field of fluid mechanics, there's a really nice review paper by Sam Tyra, who's actually a professor here at UCLA, and some other co-authors on how to extract and utilize these patterns for high-dimensional spatial temporal data. So what I'm going to talk about today is really about how we can learn differential equation models that are both interpretable and generalizable. So I'm going to kind of cut the preamble and get right to the point here. We all use machine learning on a daily basis. This is changing our world. When most people think of machine learning, a lot of times it's becoming synonymous with deep learning, with deep neural networks. And of course, these are very, very powerful tools, but these are not the only tools available to us. And so I want to advocate for some more humble machine learning techniques that give us some of what we are missing from our olden days of classical physics, interpretability and generalizability. So instead of defining these, I always get into fights when I try to define these. I'll just give you my favorite example of an interpretable generalizable model. So Newton's second law, F equals ma, is clearly interpretable. It has 3 terms, force, mass, and acceleration. They have units. You can write these down for a particular problem of interest and go to a coffee shop with a friend and analyze and discuss them. They're highly explainable and interpretable. And they're generalizable in the sense that you can learn F equals ma from an apple falling on Earth. That's how the story goes. And it's still valid when we land humans on the moon. That's the ultimate generalizable model. Now, of course, you could train a deep neural network on videos of apples falling. You might need 1,000 videos of 1,000 apples falling, and it will generate new videos that will fool all of us in the audience. But that's not going to be useful when we land humans on Mars. Okay, we want models that generalize beyond where they were trained, well beyond where they were trained. Okay, and so what's the characteristic of models that generalize? We have a word for this. Models that generalize are physics models. That's a pretty good working definition of what physics is models that generalize. And so I'm trying to set up a mathematical framework for how we can promote interpretable and generalizable models in our own work in machine learning. So the gold standard of what makes a model generalizable and physical, and this is from Aristotle to Einstein for 2 millennia in physics, is to find the model that's as simple as possible, but no simpler. That's Occam's razor, that's the Pareto optimality, that's the principle of parsimony. You want the simplest model possible, but no simpler. And that has been the gold standard for what is physical, what models probably are likely to generalize beyond where they were trained. Now, you might disagree with me. That is very much different than the perspective modern times of over-parameterizing models and having models that are as complicated as possible. And I think there's room for both of these perspectives. Okay? So again, in the modern era, we have two very powerful mathematical tools to promote these kinds of models when we're doing machine learning. The tools of low dimensionality. So even when I have very high dimensional complex systems, I want to find the fewest patterns that describe the things I care about those systems. So I want low dimensional patterns. And I want sparsity. If I'm going to write down a differential equation that describes how those patterns co-evolve in time, I want the simplest differential equation that describes my data and no simpler. Okay? That's the setup. So that's what I'm going to show you today. And again, if we fast forward from Isaac Newton and Einstein to the modern computational era, this starts to look a lot like the Lorentz 1963 model for chaotic thermal convection in the atmosphere. So this very, very simple model, notice it has the two hallmark features. It's low dimensional. It's written in terms of 3 variables, x, y, and z. These are the amplitudes of 3 spatial modes used to describe this unsteady fluid flow. They were proposed by Saltzman a year earlier. So it's low dimensional, and it's sparse. Out of all of the possible right-hand side differential equations you could use to describe this observed phenomenology, this is a very simple differential equation. There are 7 terms, 5 of them are linear. Okay, so low dimensional, sparse, this is the kind of model we want. And it describes a pretty rich phenomenon, right? This is used to model chaotic kind of weather patterns in the Earth's atmosphere. So I'm going to set up how we can start to learn differential equation models that have those 2 features using relatively simple tools in machine learning. I'm going to start really, really simple, and then we're going to build complexity as we go. I should have mentioned, if you have any questions at any point, please just jump in and interrupt, okay? So I'm actually going to warm up on the Lorentz 1963 problem. It's a really easy toy problem to code up, and it's a pretty fun problem to play around with. So this is an algorithm we call the sparse identification of nonlinear dynamics, or SINDy. How many of you have heard of SINDy? Okay, how many of you have not? That's helpful. Okay, about half, perfect. So I'll do a quick overview and then I'll get into some advanced stuff for the people who have seen it. So the idea is that we have data from this complex system. So this is a differential equation generating data, time series of x, y, and z in time. And let's say I can compute their derivatives as well. I can approximate their derivatives or measure the rates of changes of things. And I'm trying to build, so I have the data, but I don't have access to the equations that generated the data. I'm trying to discover those equations. So what is the simplest model I could think of to describe time series data? Like we're trying to adhere to that Einstein quote. What's the simplest model possible that could describe the data? Yeah, so constant's definitely the simplest. Linear would be the simplest reasonable model I would try. I mean, if I can get away with x dot equals 0, I will. So the dynamic mode decomposition, which many of you have heard about, this has been around for 10 years, tries to fit a best fit little linear 3x3 A matrix model that best fits the derivatives x dot y dot z dot in terms of the states x, y, and z. But we know that this is going to be too simple. This is overly simple. So this A matrix, this linear system has a single fixed point at the origin. My Lorentz system has 3 fixed points, infinitely many unstable periodic orbits, and a strange attractor, right? It can't possibly capture this phenomenology with the simple linear dynamics in the state variables x, y, and z. So what we do in SINDy is a very, very simple idea, is we augment the right-hand side with more possible terms that could describe my dynamics. Here I've chosen polynomials up to z to the 5th. You can choose anything that it's up to your creativity. You can use sines and cosines, Bessel's functions, rational functions. It depends on the physics you're looking at, how you build this library. I'll show you later that for fluid flow systems in general, and any kind of continuum mechanics systems, polynomials actually do a great job because those are the models we get when we do Galerkin projection. So in this case, we're doing polynomials up to 5th order. And so the objective of SINDy, if I just did a least squares regression here, I could just do a best fit, and I would get a little bit of all of these coefficients being active. A little bit of all of these terms would be in my differential equation. That would clearly be overfit to the data. I don't want a differential equation with 81 terms in every equation. So instead what I do is I try to find the sparsest combination, the fewest columns of theta that add up to x dot, that add up to y dot, and that add up to z dot. Okay? And that sounds easy. It's really easy for me to say the sparsest combination or the fewest terms in theta. 20 years ago, that would have been an NP-hard brute force search. That is not in general a convex optimization problem, but in the last 20 years, there have been huge advances in sparse optimization, and now there are dozens of commodity algorithms that approximately solve that problem. We came up with our own for this 2016 paper. In fact, I'll tell you a little bit about how we do it. It's pretty interesting, and it'll be relevant later. What we do is we first do a simple least squares regression, so we get a little bit of all of these terms active, but some of them are small. And so we threshold those. We do a hard threshold. Then we do another least squares onto the remaining terms, and it kind of fixes those, and some of those become small. And we threshold the small terms again. And we iteratively do this until we converge on this sparse nonlinear model. And you'll notice that the terms that are highlighted in the x dot, y dot, and z dot equations are in fact the actual terms that were in the differential equation that generated the data. So of course, this is what we call rediscovery. We already knew that equation. We used it to generate the data, but this is a good sanity check when we want to test an algorithm. We should always try it on things where we know the answer to see if it actually works. Okay. Good. Any questions about this before I move on? Yeah.
Maybe it's obvious, but what if it's non-autonomous?
Yeah, so I'm showing the vanilla kind of baby version. You can add all kinds of interesting things to this library. You can add time dependence, so you can add literally products of t times x or sine of t times x or whatever. You can add control inputs if you have actuation and control. You can add bifurcation parameters, some beta parameters that control, the Reynolds number or the Mach number, and we've actually done most of those things in this 2016 paper. Yeah, yes.
I actually just have a question about this particular system. So it seems that X, Y, and Z each mean something very different. So in a physical system, if I wanted to use this and see if my system looks like this, how would I choose my X, Y, and Z?
That's a fantastic question. That's there's a few main issues you have to address when you're doing this. The first one is choosing what variables to measure. X, Y, choosing the right measurement variables is the most important step. Then choosing the right library that could describe the dynamics is maybe the next most important step. The sparse optimization is the easiest step at the end. So choosing the right variables is very problem specific. So we are fortunate in fluid dynamics and in continuum mechanics in general that usually we have our high dimensional data, and if we just collect snapshots of that in time and compute the singular value decomposition, that gives us a pretty good basis in which to represent. So X, Y, and Z here could be the amplitudes of the first three singular vectors. That's always a good place to start. You could use an autoencoder to find these coordinates if you have high dimensional data. So my wife Bing is a neuroscientist, and we're trying to figure out how to apply this to neuroscience data. It's really hard. What is X, Y, and Z for the brain? We don't know. So that's something I'll get to in a little bit, but great question. Thank you. Great questions. Other questions? Okay, so that's the basic setup. This is rediscovery. Obviously, we already knew the answer. So if the story ended here, this wouldn't be a very good story. I'll show you some cases where we've discovered things we didn't know. Just a plug for our software, SINDy. This is a pretty well-maintained open source software package. If you want to try this out on your time series data, you can do this. This is also has tools for discovering partial differential equations.
Sorry,
oh, yeah.
It seems there is a connection with compressed sensing and all the sparse convex optimization developed at that time.
Yeah, so we actually cooked up the algorithm in 2015, and for the 4 years before that, I was working mostly in compressed sensing. So that's exactly right. So this kind of compressed sensing idea of finding sparse vectors for these underdetermined systems, and I tried using compressed sensing to solve this problem, and it failed when we added 10 to the minus 14 noise. Because this is not an underdetermined problem, this is an overdetermined problem. So I've got less coefficients than I have time series points. And so actually this is an easier problem that had been solved before compressed sensing. So this is more like the lasso problem than the compressed sensing problem. But you're absolutely right, it's deeply connected to high dimensional sparse geometry. And we've had a lot of follow-up papers where we've explored that.
So because you mentioned lasso, that was exactly my question. So as I understood, you are enforcing sparsity here in an iterative manner.
Yes, so we're not using it's morally like the lasso, but we have our own algorithm that is a sequentially thresholded least squares algorithm. And the reason we do that, I'll give a teaser for later, is that when I do a least squares at every step, I can enforce constraints I can do constrained least squares. So if I know that there are symmetries that should be adhered to, I can hard constrain those symmetries to be enforced at every step of that process, which is harder to do with other sparse optimization. Okay, great questions, thank you. Okay, so you can also use this to discover PDEs. This is, we've been just getting more and more excited the more we develop this. So this is work by Sam Rudy when he was a PhD student with Nathan and me. And Sam realized pretty quickly that you could also use this technique to discover partial differential equations instead of just ordinary differential equations. So here we have fluid flow past a cylinder. This is our toy problem in fluids. And what Sam did was build the same library regression procedure, but now you'll notice that you have partial derivatives and nonlinear products of partial derivatives. So you do, again, have to choose the right variable to model. So we know that we want to be modeling, let's say, the time derivative of vorticity. That's a reasonable thing to model. And we're going to try to find some sparse combination in this library that describes that quantity best. And when you run this essentially iterative thresholded least squares procedure, the identified dynamics you get are here. This is the actual model Sam got. It is the coordinate form of the Navier-Stokes equation, and the Reynolds number is learned to within about 1% of the true value. So it's pretty good. And I'll point out, this is actually a secondary point, is that because spatial temporal data is so vast, there is so much of it, you can often get away with dramatically downsampling in space and in time. As long as you have large enough patches to compute derivatives, you normally get the right dynamics even from dramatically subsampled data. So since this 2017 paper, we benchmarked this on maybe 10 PDEs where we knew the answer. Again, we always start with rediscovery before we go to actual discovery. And in all of those cases, we were able to relearn those PDEs even from noisy measurement data. In the intervening years, we have made this much more noise robust. So now we have ensembling techniques that make it way, way more robust to noise. Other authors have introduced weak formulations and integral formulations that make it a lot more robust to noise. And I'll point out, sorry, I'll take your question in just a second, that people have actually started using this for real scientific discovery. So that's what gets me super excited. I'll just give you kind of the rundown of the things that people have used this for in the last 5 years. So turbulence closure modeling. There have been maybe half a dozen papers using this to find new closure models for the Reynolds average Navier-Stokes equations and for large eddy simulations. So Sarah Beetham and Jesse Capisalatro, Schmelzer, Laura Zana from NYU, they've all had really interesting new closure models that have, in some cases, symmetries that we know the system should adhere to built in, which is pretty cool. Plasma physics. So Paulo Alves from UCLA has used this to take particle in cell, very high fidelity simulations of plasmas and get extra terms in the magnetohydrodynamics equations. So I didn't know this earlier. The incompressible Navier-Stokes is a very good representation of incompressible fluid flows. It's an almost perfect mathematical model. Magnetohydrodynamics is not as good of a model for plasmas. It has deficiencies. And so researchers are using high fidelity simulations to build new closure terms for those models. Researchers at Georgia Tech, Roman Grigoriev and Mike Schatz, are using this for active matter and rheoscopic fluids. And in my lab, we're using this to model neuroscience systems and coarse graining of things like granular materials. So it's pretty cool. We're actually getting real new PDEs that have never been written down before. Yeah.
When you say simulations, do you mean microscopic simulations or something like this?
I mean more like microscopic simulations, yeah. Yeah, so they actually track individual particles in a grid. So super expensive computations, and they can only do it on very small little patches. But again, if I had a little patch of fluids, it still is governed by the PDE, and so I can generalize based on that. One question here first, and then...
Yeah, I was wondering if you do the other approach, so taking experimental data or something, measure it to obtain the PDE that governs that phenomena.
Yeah, sorry, I should have mentioned, in some of those cases, these are experimental data sets. So Mike Schatz and Roman Grigoriev at Georgia Tech, they're actually taking experimental fluids data to do this. In our coarse graining of granular materials, we actually have a physical apparatus to be shaking these particles and collecting measurement data. In neuroscience, these are actual calcium imaging recordings or imaging of the retina.
And a follow-up question, how do you deal then with experimental noise, these types that might be overfitting sometimes?
Yeah, I mean, so sparsity is a pretty good way of preventing overfitting. So, sparsity is one of our leading strategies for confronting noise. Another one is ensembling. So you basically bootstrap your data, take 80% of your data randomly, build a model, do that 1,000 times, and then you actually get inclusion probabilities for these coefficients now. So I know the probability of a coefficient being active or not. That has been a game changer. So that's worked by Urban Fazell when he was a postdoc with us. Now we can handle, 100% noise instead of 1% noise. I mean, I don't have a slide on that, but it's quite impressive. Yeah, there's a question.
The quick question is that the identified dynamics D is this kind of coordinate form. I'm just like, is it, it's not an important question, but I mean, if you, either through kind of enforcing a symmetry or in the way that you set up the library, I mean, can you have it to where it just learns the kind of more traditional? Or is it somehow annoying?
So that's a great question, and I actually have been hounding my students because they always use the simple version that spits it out in the coordinate form, and I tell them, well, hey, just use grad operators instead of in principle, you can definitely set this up so that it will spit out more human readable equations. I think kind of like the vanilla version usually just has a list of terms, but you can absolutely do that. Especially, I mean, I want to point out this is not an automated discovery tool. Like we always thought it would be at first, like you put your data in, you turn a crank and you get models out. That's not how this ended up working. This is a tool for scientific experts to build models. Like if you think that you could build a model, if you had enough time and enough paper and pencil, this will help you do it faster. And so to some extent, the human needs to look at these occasionally and say like, oh, well, that's clearly Laplacian operator. Like I can just write that down. So there's a little bit of back and forth, presumably, with the human expert. Great question. Yes?
Are there any theoretical guarantees on the amount of data you need to get a certain accuracy in your reconstruction? Yeah,
that's a really good question. So this is a bit outside of my expertise. I know a little bit about this. So there certainly are lots of theories on when this will and will not work, this sparse regression problem, for the lasso problem in particular. So it's very well studied for lasso. And in fact, we found some really good papers by Joel Trop in the 2009 timeframe where he provides conditions for exact recovery of the sparse regression problem on the data size, the library condition number. There's a generalized condition number for sparse regression problems. And so there are ways to quantify when this will and will not work pretty well. We found that those are fairly conservative bounds, and we have a lot of heuristics for when this works well. Like you want a good diversity of data, you want transients, you want to sample off of the attractor. All of those things are going to help this converge faster because it's kind of, roughly speaking, improving the condition number of this matrix. And the condition number of that matrix, roughly speaking, is going to give you an idea of how good of an estimate of C we get in each of these least squares steps. So we have really simple heuristics for how to improve that condition number, but there are 100-page texts on like proofs of how this actually will converge by other people. Yep. Yeah, in the back.
Maybe a bit pragmatic, but what about non-constant coefficients? What if my P behaves differently in different regions? What about boundary layers, etc.?
Yeah, so that was Sam's second paper, actually. So you can use something called the group lasso across your data so that you will have the same sparsity pattern, but those coefficients can change in time. So you can definitely have coefficients that change either in time or in space. Typically, you would do this over patches. I'll show you another example of this later. That's a harder optimization. Very important for neuroscience. Even if I think that there might be some drift diffusion dispersion model for my brain, presumably the coefficients are changing everywhere based on material properties and connections and things like that. Yeah, really good point. Okay, excellent. Great questions. So very high level summary, we're trying to get dynamical systems from data. These typically come in the form of ODEs or PDEs in my experience. So if I have a system like the Lorentz 1963, I want a low-dimensional sparse system of ordinary differential equations. If I have spatial temporal data, I want something like a partial differential equation. Okay. There is a third option. So this is where I'm going to show you maybe the next 10 minutes or so. There's a third option, and this is actually what Lorentz did to get this ODE from his spatial temporal system, is that if you have a spatial temporal system, typically what you would do is you would actually break it down into some low dimensional modal basis. So this is how we choose X, Y, and Z, is compute the singular value decomposition or the principal components of this flow to get a few modes in a basis that describe that. And then we're going to model the evolution of the amplitudes of these modes, X, Y, and Z. Okay, and so that's, yes?
As you know, I tried to play with all of this, but we got stuck into the when adding stochasticity.
Yes.
Becomes really difficult.
Yeah, so stochasticity is one of, I might have some backup slides on that. So we have extended this to turbulent wake flows, building on your stochastic version of SINDy. So essentially you can add stochastic forcing terms here. I think
it's very brittle. It works for only very low dimension.
So I think our approach, we didn't suffer from it being brittle, but we did suffer from it being low dimensional. Like we couldn't learn models that were higher than 3 dimensions with stochastic forcing because we're now trying to fit distributions. But we did find that for a Reynolds number 1 million turbulent wake, we actually were able to get a 3-state model for that, which was surprising. I didn't think it would be possible. So stochastics is hard, but possible in low-dimensional cases. Yeah, really good point. Thank you. Okay, so I'm going to talk about this kind of bottom row now of how we get these. These are what we call reduced order models. So these are low-dimensional ODEs that are tailored to a specific kind of geometry of a PDE we're analyzing. And this model here is actually the famous 2003 Barrett-Nowak model for this flow. So this is one of the most famous models in fluid dynamics. And I'll show you how we can learn it from scratch. Okay, so the idea, again, is you take your spatial temporal data, compute the SVD to get a few modes in a modal basis. And if you write your system in these 3 variables, so the amplitudes of these 3 modes, then your data essentially looks like this black curve that lives on a slow parabolic manifold. This was observed by Barrett-Nowak and colleagues in 2003, 20 years ago. And this is the model that they obtained by literally taking the Navier-Stokes equations and Galerkin projecting them onto this orthogonal basis, standard model reduction, okay? And it's a beautiful model. This solved a lot of issues and open challenges that have been around for decades of how you can get a cubic Hopf bifurcation in a quadratically nonlinear fluid system. So by having a timescale separation where the z variable is much faster than x and y, z will rapidly equilibrate to equal x squared plus y squared. And if I plug that in here, I get the effect of a cubic nonlinearity. This is kind of like the Stewart-Landau mechanism. So famous paper, really, really elegant stuff. We decided we would take this flow, measure it in these coordinates, and run it through the SINDy algorithm. And when we run it through the SINDy algorithm, we learn this model. This is the model that pops out, is the one that Barrett-Nowak got from Galerkin projection. So we didn't need the governing equations. We didn't need a working CFD code. We didn't need to do any of those steps to find this model and this timescale separation. And you see that our identified system also has the slow manifold and fairly accurately captures the nonlinear dynamics of the system. This is when we started getting pretty excited that you could actually use this for real problems that had, this was the Nowak paper, that solved a 15-year debate in the community, okay? So within about 2 weeks of writing this paper, I got an email from my now very close colleague, Jean-Christophe Loiseau. He was a postdoc at KTH at the time. Now he's a professor at Paris Tech. And he said, well, there's some real issues with your model. There are, the coefficients are wrong, the linear growth rate's wrong. Things that matter to him as a fluid dynamicist were not completely right in our model. And so he emailed me back 2 weeks after that, and he said, okay, good news, I fixed it. And so I'm going to tell you one of my absolute favorite stories. So JC is brilliant and has been a pleasure to work with. And he has 2 of the best innovations to this algorithm that I want to tell you about today. So the first one, I think, is very relevant to you all. Because of the way that we enforce sparsity in our model by doing a sequentially thresholded least squares, We can add constraints at every stage of every time we do a least squares, we can add constraints. Very, very simply using a KKT least squares, we can add constraint equations on those coefficients C that we want to be sparse. And so we know a lot about incompressible fluid flows. We know that they conserve energy. And more than that, we know that they conserve energy because of a skew symmetry in the quadratic nonlinearities. Okay, this is from the Navier-Stokes equations. And that's a very special kind of partial knowledge. It doesn't tell me anything about how the coefficients are going to be for this very particular flow, except that all of the quadratic nonlinearities have to be skew symmetric. And so I can add 10 constraint equations, well, JC added 10 constraint equations, and immediately our models are guaranteed to have that symmetry enforced, all of them by construction, which dramatically improves stability of the models. So I'll show you some numerical results in a minute. The second key innovation, when we wrote down this first SINDy model, we were searching in a quadratic library because the Navier-Stokes have quadratic nonlinearities and because that was the interesting storyline of how you get cubic phenomena with quadratic nonlinearities. But what JC pointed out is that if you include higher order nonlinearities, cubic, quintic, septic, nonic, third, fifth, seventh, ninth order terms, you can account for very low energy modes that you've truncated in your Galerkin expansion. They dynamically affect these energetic modes as higher order nonlinearities. And so in a very real sense, what that does is it gives you a closure model for the truncated energy and how they affect these high energy modes. By adding higher order nonlinearities, we get a closure model. Now, I should be very cautious, right? Like closure is a loaded term and it's one of the hardest problems in fluids. This is a laminar problem, but for this laminar problem, we're getting closure models. Okay.
Quick question about that equation because
yes.
I have a hard time parsing that. So
this one or this one?
Yeah, the left one. So
yep.
Z and C and Xi only appear on, and D only appear on the right hand side. Doesn't have to seem any relationship with the left hand side somehow.
Yeah, so the left-hand side is trying to get a good model fit. So this Xi, so we're optimizing essentially over Xi to get a good model fit. And then I guess you can think of these as Lagrange multipliers to satisfy this set of constraint equations. C times Xi equals D.
Oh, you mean this? The small Xi is related
sorry,
to the
columns of the big Xi.
Oh,
yeah, sorry about that. Good catch. Yep. The notation's a little messy because we're dealing with systems of ordinary differential equations, so we have a little Xi for every equation, which stack into a big C. Yep. Good question.
In terms of your story, like on the right, this is the same equations you had before, right?
Yeah, I'm just throwing up the original ones. JC's model now has plus cubic, plus quintic, plus septic, plus nonic, higher order terms. He actually went up to like 17th order to get better closures.
And so so you include those terms and you find it by including this additional skew symmetric constraints and things like that, and then when you run the whole thing, it
works way better.
Works better.
Yeah. Yeah, so that's what I'll show you in the next slide, actually.
You chop off the other stuff that's like the closure, you still have these kind of original, or did that gets modified?
So I'm going to show you two different versions of this. If you just enforce these constraints and keep the model quadratic, it works really well. If you don't enforce these constraints, but you have higher order terms, it also works really well. So actually both of these work, and if you combine them, it works even better. Yeah?
I couldn't get it from context. Could you just give a simple definition of what you mean by closure?
Closure, yeah. So essentially, in that step where I computed the singular value decomposition, let's say back here, these first two POD modes count for about 96% of the energy or variance of this flow, but there are higher order POD modes that are higher frequency and faster and have their own dynamics. And I've just chopped those off and neglected those. So the true equations, I would need to keep track of a differential equation of all of those, but I'm just chopping off, all of those low energy modes. And that messes up the dynamics of the high energy modes. So that's the closure problem. How do I account for those dynamics in the large modes without actually modeling them? And that's what JC pointed out, is that by having higher order equations here, that can give you a closure for those terms. Yep, good question. Okay, so I'm going to show you some numerical results. So these are, again, two relatively simple flows. We've tested this on more sophisticated flows since then, but these are easy to understand. So cavity flow and cylinder flow. This column here is the kind of previous industry standard state of the art. Okay, so A delta, the y-axis here, this is what we call that shift mode. It's my third variable, z, and it's a pretty good proxy for the drag coefficient. It's something I care about as an engineer. I want to model this, okay? The white curve is the ground truth from a high fidelity numerical simulation. So an expensive simulation gives me this white curve as it evolves in time. Yellow and blue are the previous Galerkin projection models where you Galerkin project Navier-Stokes onto either 3 or 7 orthogonal modes. And you'll notice that they are qualitatively okay, but quantitatively pretty inaccurate. They have the wrong rise time, the wrong kind of linear growth rate. They have overshoot and significant steady state error. These are quantitatively inaccurate. And this is what we were working with before. When we do SINDy, either by including these constraints or by having higher order terms like cubic terms, we get almost perfect quantitative agreement for this quantity of interest. These are models with 2 states. These are 2 coupled differential equations, first order. Much, much more accurate. Now, accuracy is good, right? I like to do control theory and modeling, and so I always want my models to be accurate, but that's not why I love these models. Why I really like these SINDy models is because they are simple. They're sparse by construction. So you can take the model that you learn and write it down on a napkin and take it to a Parisian coffee shop and analyze it. That's what JC did, and you come up with this. This is the model JC got. This is the model that gives you this picture-perfect accuracy for this flow past a cylinder. It says that this flow can be very well approximated by a spring mass damper with a nonlinear damping coefficient. This is a van der Pol oscillator. This is the simplest model that's been written down and the most accurate model that's been written down for the cylinder flow. And it's because of sparsity, right? So accuracy is great, but sparsity is the key here because we can communicate and understand and discuss what this model is doing here today. Okay, you can't do that easily with a Galerkin model. Yes?
How easy is it to interpret like the meaning of specific coefficients in terms of like material properties or fluid properties?
Yeah, so that's actually that's a really good question, and that is what got JC interested in this in the first place, was that the coefficients of those had physical meanings, and he could identify, oh, this one's not right, we need to fix this one. So, for example, this like linear growth rate is a very important property of the fluid that has to do with the bifurcation parameters like the Reynolds number and things like that. So there are definitely things you can read off of these equations and tie them to physical properties for sure.
In your simulation, like, can you point to what like parameters that you put into your simulation to generate this data?
In principle, you can. Yep. Yes, absolutely. JC could. So yeah, JC definitely could. Okay, good. So something else I'll point out here is that this was a follow-up work the next year where we looked at a more complex flow. So this is what we call the fluidic pinball. So there's 3 cylinders here. You get more broadband kind of turbulent phenomena. What we did here was we pretended that we did not have access to the wake measurements, right? So when Boeing and Airbus are building models, they're not going to have full 3-dimensional wake velocity measurements over their wing. They're going to have maybe a few pressure measurements. So what we did was we only measured lift and drag on these 3 cylinders. So we have 6 measurements in time. And we saw, can we build a SINDy model just in lift and drag coordinates on those surfaces? And so here in the bottom plot, you actually see the results of this. These are a few transects. DNS is our high fidelity simulation. Blue is our low order SINDy model. You get an almost perfect agreement here, again, with a sparse nonlinear model in these intrinsic lift and drag coordinates. So this solves a lot of problems we have in fluids. I'm not going to bore you with the details, but in the old way of working where we compute a singular value decomposition for our basis, if I deform my wing or I change my flow velocity or I move my immersed body, all of that breaks my POD, my SVD modes. Like these modes don't mean the same thing when I move my geometry. But when I build models in lift and drag, those variables always mean the same thing. They're intrinsic coordinates in a sense. And so I can build those models across parameters and actually have them talk to each other. So it's a big deal for us in control. I'm just going to give you more vignettes and then pull back in a minute. So I want to talk about symmetries because I think this audience cares a lot about symmetries. I care a lot about symmetries, and I don't get to talk about this a lot with my fluids people. So originally, we were looking at this chaotic thermal convection problem for the Lorentz 1963. There is another type of convection, which is electroconvection, which has a more complicated three-way coupling. Instead of just coupling temperature and the fluid flow here, we're coupling the fluid flow, the charge density, and the electric field. So you can get some pretty exotic behavior here. There's a lot of technologies developed around electroconvective cells today. I'm not an expert in electroconvection, but fortunately Igor Novoselov and Yifei Guan are. And so what we decided to do was see if we can model this flow in the same way that Lorentz modeled the Rayleigh-Benard convection. So I'm going to walk you through this process. It's kind of interesting. So the idea is you have a time series of data. These are kind of high-dimensional flow fields, if you will. They're spatial temporal data. We compute the POD or the SVD to get a low-dimensional basis. This is usually what we do. And then we look at the amplitudes of those modes as they evolve in time. So A1 is the amplitude of the first mode, A2 is the amplitude of the second mode, and so on and so forth. And we usually plot them like this, A1 versus A2, A1 versus A3. So right off the bat, you can see that this is complicated and has deep symmetries. Okay, if I plot this in 3D, this is what A1 versus A2 versus A3. And these are, again, the coefficients of those modes as they evolve in time. So we tried to develop a SINDy model for this data without enforcing the symmetries, and we got all kinds of weird, degenerate problems. Our models fit very accurately the derivatives, but when we integrated the models, they didn't have the right behavior at all. And so I pressed Yifei, this was when he was a PhD student at UW, to start uncovering and actually writing down the symmetries that we can see by eye, and using that to constrain the library regression procedure further. So essentially using that constrained formulation I showed you before, we can get an almost perfect skeletal model of these dynamics. It doesn't have every detail, but it has the broad features, and it gives us very, very good predictions. So I'm going to zoom in for a minute. So lots of systems have these kinds of symmetries where you can, mirror and flip some variables like this. And so these are the 5 that Yifei painstakingly identified just by looking at these plots. And if you have these 5 symmetries, you can actually deduce that in a cubic SINDy library, you can kill most of the terms. All of these black boxes here are terms that can't exist and have those symmetries. And you can also further dramatically constrain the coefficients that are remaining. So for example, you'll notice there are 4 terms here that are all related to C2. And so those all have to be kind of the same value, plus or minus, to adhere to these symmetries. So by enforcing these symmetries, we were able to get a very, very accurate model, again, that has the same kind of chaotic loop structure. It has the same chaotic dynamics, very good reconstruction of the actual flow fields and the skeletal dynamics. Just one second. I'll point out, we also need much less data when we enforce these symmetries because you're fitting way less parameters. Yes, question?
So these are the symmetries, I guess, in the coefficient space. But
yeah.
What does that correspond to in the physical space?
So that is exactly the question I asked Yifei, but he graduated. He was not my PhD student. It's a great question. Like that is the question I want to know. So Yifei was Igor's PhD student. I was just working with them, and I have always wanted to know that. And I think that is maybe one of the next directions we should take this in, is inferring from the spatial temporal symmetries what the coefficient symmetries are and vice versa. I think that's an open question.
You could build a library of that, I guess, right? Some symmetries are, just spatial symmetries. You could just build them in and just see if, try them out somehow.
Yep.
But depending on how you do your SVD or whatever, they might turn into different types of symmetries in your coefficient space.
I think it's a really astute observation, and there is quite a lot of classical theory in the Galerkin projection literature about how symmetries in like spatial symmetries will relate to the differential equations that you get. We have not really leveraged that yet, so that's definitely an open area of, yeah, absolutely. Yes?
Do you suspect that it's a symmetry more complicated than just like x and minus x? Like it seems like those dimensions are not distinguishable. So it's that you don't have like a type, so you have a symmetry just in the x direction.
Oh, in the actual spatial temporal field.
Yeah, I'm wondering if that's enough to actually kill most of those coefficients.
It very well might be, yeah. I don't have a lot of intuition for electroconvection and how the system works. And in fact, this is a pretty hard one to do Galerkin projection on because it's coupled multiphysics problem. But in principle, we've also done this for plasma physics systems. Maybe I'll jump to that actually. So this is like the wow slide. I've shown you a couple of these examples here. We've applied this to other systems as well. One of the systems that my former PhD student, Alan Kaptanoglu, worked on was this 3-dimensional Spheramac fusion reactor. This is a full time-resolved simulation of a 3-dimensional Spheramac. In that MHD system, we can actually derive explicitly the same kinds of symmetries that exist for Navier-Stokes, but for MHD and enforce them in this. And so again, this was constrained to adhere to certain symmetries that we know are in the governing spatial temporal system. So that's an example where the story has been more fully developed. He was my PhD student and I pushed him a lot on that. And then I mentioned before, we have developed some stochastic closure models, essentially using a modified version of a paper Cecilia wrote earlier, where you can add some stochastic forcing terms on here. Okay, good. So let's see, I've got a few more minutes. Maybe I will give you one more vignette and keep taking questions. Any questions before I keep going on? I'll just throw up my summary slide, yeah.
Yeah, so you started with this generalizability statement.
Yes.
I'm just curious that if any of these coefficients that you are considering, impose symmetry, can you use them as a warm start to show their generalizability to another, PD?
That's a really good question. So there's different levels of generalizability in each of these models. So if you learn a PDE for a phenomena, that is clearly highly generalizable, right? Navier-Stokes equations is very, very generalizable. When I'm learning a reduced order model, I am already dramatically narrowing my focus to this very particular geometry and Reynolds number. So I'm looking at a very particular flow velocity and geometry here. Again, you can build in bifurcation parameters to these. So I can build in the Reynolds number. These coefficients depend on the Reynolds number. That makes it more generalizable. Something I didn't show you is I can start with trajectories that are off of the attractor, like different trajectories or controlled trajectories that I have not used for training data. And these models tend to very accurately predict those off attractor. So it's generalizable within that same problem space. If you add in the bifurcation parameter, you can generalize outside of that problem space. Yeah. So it's kind of a moving target of what we mean by generalizable depending on the problem. Yeah, good question. Yes?
So you're using linear embeddings in some sense. Why not use a nonlinear embedding and then do your coefficients, evolve your coefficients in that nonlinear space, like some kind of VAE instead of PCA?
Yeah, absolutely. So I'm not going to have time to get to that part, but we absolutely have done that. So extending, we always started with low dimensional linear embeddings because that's what we do in fluids and it works really well for lots and lots of systems and we get nice quadratic polynomial systems. My former PhD student, Kathleen Champion, she generalized this to learning autoencoder coordinates with SINDy models in the middle. It's a very tough optimization because you can't do it sequentially anymore because the autoencoder will, there's infinitely many warped versions of an autoencoder latent space. And so you simultaneously have to learn, let's see if I can just jump ahead to that. I'd like to show you that slide if I can.
You could argue your brain has to solve that problem.
Absolutely, absolutely. So Kathleen was did a fantastic PhD on this. What she found was that trying to learn these things sequentially is very hard, again, for the same reasons. So you have to simultaneously learn the coordinates and a sparse dynamic. So you're learning a low-dimensional latent space, Z, that admits a sparse nonlinear model. And so it's a hard optimization. This was a tough one to get working, but technically it is possible. Other people have done similar things. Hodlibson's group does similar things to this. You can do this for, actually it's kind of interesting, instead of just trying to learn nonlinear dynamics that are sparse in the latent space, you can even go farther and try to say, why not learn linear models? So this is, Frank has worked on this, we've worked on this. There's this is an old slide, so there's a dozen papers at least that are trying to use nonlinear autoencoders to learn latent linear representations of the dynamics related to Koopman. It's a pretty exciting area. Like this is, you know, getting the best of both worlds of coordinates and dynamics. And maybe I'll just then give a philosophical teaser. So kind of this is the philosophical reason why we think this is so important. You know, I was talking about F equals ma at the very beginning. When we look up at the night sky from our little blue dot, this is what we see. It's very complicated, right? The planets do crazy things. Sometimes they turn around in their orbits. It's very hard to model the planets. That's why we name our gods after the planets and our planets after the gods, because they do what they want. Okay, it's hard to learn F equals ma in this coordinate system. When you get the right coordinate system and things become simple, that's when you can learn F equals ma. So this is just philosophically, these really are not separate problems. You have to simultaneously learn coordinates and the dynamics. This gets back to Tess, your question earlier. How do you know what X, Y, and Z are? Well, when you're looking at a new system, you know, you've got to figure out what the right coordinates are to even know what are good. Yeah, it's a joint problem is what I'm trying to say. Okay, so I think that's probably all I have time for. I'm just going to throw up a slide here and see if there's questions. And yeah, I'll talk for, yes.
This is just a clarification. I realized that I made a bad assumption about the meaning of X, Y, and Z for the bottom system. So in this case, they are orthogonal modes, and they're the highest order orthogonal modes of the above system.
Yeah, X, Y, and Z are the amplitudes of those three leading orthogonal modes. That's right.
And so if I read other papers kind of in this area,
that'll be the same.
I should assume that if they're represented by like different letters, that it means they're orthogonal, but it doesn't. I shouldn't be thinking of like Cartesian coordinates.
Yeah, sorry. Yes, this is not X, Y, and Z. And so, for example, literally, if I wanted to approximate this flow field, I would take X times this field plus Y times this field plus Z times this field, and if I added those up, I would get a pretty decent facsimile of this field.
So each of those modes actually has symmetry properties.
Yes.
Thank you.
Yeah, and there's a great book by Phil Holmes and others from the late 80s that talks about how symmetries in these modes relate to symmetries in the dynamical systems. We really haven't used any of that. We just hired a postdoc who is steeped in that literature, so we're hoping to build some of that in. Yeah.
Kind of a really naive question. So, I mean, it's all beautiful and amazing and cool. I'm trying to think about like when you do this approximation. I mean, one is to look at it and have some insight into what's going on, but from a very practical perspective, are you using it also just to try to? I mean, if you wanted to simulate the flow with this model, is it just like way faster because you're not doing
so much faster? Yeah, this is 100,000 degrees of freedom. This is 3 degrees of freedom.
But is that like one of the primary drivers for it, having that super fast approximate thing, or is it?
Yeah. So. I mean, so I've spent a lot of time in different levels of this plot. Most of my career has been in this reduced order modeling world. The reason we want reduced order models is often for things like flow control. So if I want to build a controller for a rocket or for a plane or for a jet engine or whatever, I don't have time to simulate this in real time, but I can maybe simulate this. And the timescales of fluid flows are very, very fast. If you're looking at a hypersonic rocket, we're talking milliseconds. I need to have full prediction of the future in milliseconds, so I have to use these reduced order models instead of these. That's something I never have time to talk about, but we have extended SINDy to include control inputs, and we have wrapped model predictive controllers around these models, and they're extremely effective for model predictive control. Yeah.
Does the linearity of the model somehow help with imposing those symmetry constraints, or could they similarly be applied to a nonlinear model?
Yeah, so I mean, these are nonlinear differential equations that are solved for as a generalized linear regression problem. We build a library and we do a linear regression. The linear regression definitely makes it easier to enforce symmetry constraints, like way easier. We have written follow-up papers where we look at constraints on these coefficients that are not just linear equality constraints. Like maybe I know that this term squared plus this term squared equals 1. They live on a circle. That's a different, harder constraint, but you can build those in using other types of relaxed optimization. I'm not an optimization expert, but we work with some, and they have shown us how to extend to more complicated constraint equations. Yep. In the far back? Yeah.
I guess we're all in the far back, but also, how, going back to my earlier question about non-constant coefficients, how does that change the symmetries you'd expect in your Galerkin projection? Would you still be able to apply that, or would you have to do some sort of procedure to, I don't know, some sort of coordinate transformation to get back to something that's symmetric?
Okay, that's a really good question. I don't know the answer off the top of my head. I'm trying to think of, so the symmetries that we know for this very particular problem are usually written down in a weak formulation. And so I believe that that would be true over a patch that has similar coefficients. I'm not sure I have a good answer to your question. We could probably write it down and see how it would affect it, but I don't know the answer. Yeah, good question. Rose, you had a question?
Yeah, so I mean, it's also related to the symmetry of the POD mode, because if we look at the physical space, it is easy to write down like what symmetries we have by looking at the solutions of the equations.
Yep.
Right. So, but if we're looking at the coefficients of POD mode, do you think it's possible? Because it's linear anyways, and then if we know like there's a unique projection in orthogonal basis, can we analytically write out like what symmetries we have in this equation instead of eyeballing it?
I think the answer is yes. I can't think of an example where we have done that in the last 5 years. I'm pretty sure that that was done 20 years ago. Like I think that is I think that that's possible, but I'm not an expert in that. We're trying to figure out how to do that. Yep. Good question. Yes.
What is the smallest scale system where you have been applying your model? Because you mentioned neuroscience and using like the brain, so I was wondering to what level this is still applicable if you try to go down.
Like what's the smallest size scale or the number of dimensions or? Well, so we have some tabletop experiments that are yay big. We have a high-speed camera. We have a bunch of little ball bearings in a dish, and we shake them. And so those have some of the properties of a fluid and other properties. And so we're essentially trying to get coarse-grained equations for these shaken granular systems. Those are pretty small. My wife's systems in neuroscience, we have data from developing mice brains. Those are very small. So like a mouse is small to begin with, and developing baby mouse is very, very small. So 1 centimeter by 1 centimeter. There's also retinal waves. We have data from retinal waves, and that's as large as a retina. So pretty small. But these are they're high fidelity spatial temporal data sequences at this point. Yeah, good question. Okay, I want to be respectful of your time. It is right on the hour. Yeah, so thank you all so much. Happy to chat more. Really appreciate it.